important stuff for just, life or whatever. We did unit conversions last time. You might have a multiple choice question on the next exam on the 10th about estimates and order of magnitude. When you're doing this, you need to be able to estimate different measurements. And so you need to know what a meter is. It's about 3 feet. You need to know what a centimeter is. It's 100th of a meter. Your pinky is a good guide for a centimeter. Most of our pinkies are about a centimeter. Those of you that work out a lot over the right center, your pinkies might be bigger than a centimeter, but many of us, our pinkies are about 1 centimeter across. So, and then you also need to know a kilogram. A kilogram is roughly how many pounds? It's 2.2 actually. It's about 2 pounds. So you need to have just rough ideas of what those things are. And so some questions that I might ask, if you look back at the old exams, you'll see. But I'll ask you, what is the area of the screen, or what is the volume of this room, or what is the volume of your head, or the length of a certain thing that you might have, some physical object that you'll either have in your hands or something that you'll be able to see very obviously in the room, okay? And in the course of that, you'll need to know the meter, the centimeter, and the kilogram. When we do order of magnitude estimates, we're really only trying to get within a factor of 10, and we'll do a couple now just to give you an idea of how they work. This is sort of grade school type stuff, like they teach grade schoolers this, but it's something that adults just aren't very able to do. It's a skill that a lot of people don't have. Even though it's taught early on, it's something that people don't know how to do very well. So let's start first with the volume of this room. Let's do this as a clicker question. Okay, I'm going to give you some options for the volume of this room that we're currently in. Is the volume of this room A, 5 cubic meters? Is it B, 50 cubic meters? C, D, E, and all by orders of 10. Is it 500 cubic meters, 5,000 cubic meters, or 50,000 cubic meters? So look around the room. You can talk to one another if you like, and ask yourself, well, how wide is the room, roughly? How long is the room, roughly? And how tall is the room? And then you can calculate the volume in cubic meters. Sometimes, by the way, I might ask this question in cubic centimeters, in which case you'd have to convert that cubic meters to cubic centimeters, as we did last time. So you first want to calculate the area, and then multiply it times the height of the roof. So let me start your clickers. And guys, everybody's registered on your clickers, so this afternoon I'll go ahead and upload a value for your clicker points. The value that I upload won't be your class participation. It's just going to be a number that says, have you answered in with your clicker or have you not answered in with your clicker? And if you don't have a number there, then please let me know and we'll take care of it. I think everybody has a clicker now. Is that correct? Anybody still waiting to get one? No? A cubic meter is roughly like a cube this shape. So how many cubic meters are there in this room? All right, we'll just go about 105. There is one person that hasn't clicked in, so make sure you get clicked in. I think that's right. 3, 5, 8, 11, 15. There we go. Let's see, C, 500 cubic meters. Let's see, roughly how wide is this room? 15? Really? It's not quite 20, maybe more like 10. These tiles are about a meter, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's just say 10. How long do you, if this is 10 meters, how long is the room? Yeah, let's just say 20, right? It's roughly twice as long as it is wide. Remember, we're just looking for order of magnitude estimates. So we have 10 across, 20 back, so that's an area of what? 200, right. And so the height of the room is roughly what? Okay, it's not quite, yeah, maybe 3 meters. Yeah, about 3 meters, you're about right. Because I'm about 2 meters, and then we got another meter on top of me, right? So that's 20 times 10 times 3, which is right. So it's we get about 600, but we're looking for an order of magnitude estimate. We just pick the closest number, which would be 500. So that's correct. You could see this in terms of centimeters as well. Something in, like, say for example, ask what's the area of your paper in centimeters, what's the area of your hand in centimeters, and they're going to be answers that are all off by a factor of 10. So clearly 50 is not the right answer here, and very clearly 5,000 is not the right answer. The room would have to be 1/10 or 10 times the size that it is now to have either of those answers, and that's just not the case. All right? Best way to practice this is to practice it. So there are some questions on the old test. You can take a look back at those, but you need to know a centimeter, a meter, and a kilogram, which is a couple pounds. Y'all good on that? I think y'all are probably okay. My one-on-one class has trouble with this, but I think, yes? Are we okay with this? All right. There are also some homework problems about this. Let's try this quick test, and then we'll move on to the next thing. What is the area of this screen?
Is it with the top white or just where it's projecting?
We can exclude the white part, sure. Just looking sort of for the closest answer here. All right, just a few more seconds. When I gave this question, actually, we were in the Pelcher Auditorium, so it was a much bigger screen. B is the correct answer here. Roughly, we have about 3 meters across, a little more than 2 meters up. Get 6, 7 meters squared. So we just round that up to 10. If you saw something like this on the test, it would be a little more obvious. Like the answers might be 6, 60, 600, and 6,000, something like that. Something that's going to be very obvious when you find the answer, and the others will obviously not be correct. Okay. All right. Let's look at coordinate systems. You should have had coordinate systems in high school math, or you probably had it since you come to Nichols, maybe. But we're just going to review it a little bit. We're going to use 2 different coordinate systems. We're going to use the Cartesian coordinate system, and then we'll also use the polar coordinate system. The Cartesian, of course, uses x, y, and z coordinates. So if I have a coordinate, like here I have the coordinates 2, 3, that means that I go over 2 on the x-axis and up 3 on the y-axis to give me that point, 2, 3. We use a right-handed coordinate system. That means that left is negative and down is negative. All right, so it's a right-handed coordinate system. Left is negative and down is negative. In this class, we'll also use a 3D coordinate system quite a bit, where we use the z coordinates as well. For the z-axis, we often draw it like this, where the z-axis comes out of the page. And on the right-handed coordinate system, we have, this would be our positive directions in the right-handed coordinate system. Up is the y-axis, that's positive. Right on the x-axis is positive. And out of the page for the z-axis is positive. So anytime we talk about a plus z direction, that's coming out towards you. Like Jaws in the 3D movies, right? That's in the positive z direction. Have y'all seen Jaws 3D? They didn't have like a remake or anything, did they? Did they? Okay, anyway, that's in the plus z direction. Y'all seen coordinates like this before? Yeah. All right. We'll also use the plane polar coordinate system. And that, instead of using coordinates x, y, and z coordinates, to use the coordinates r and theta, we'll just use a 2-dimensional plane polar coordinate system. Although there is a 3-dimensional where you use r and then 2 separate angles to define a point in space. But we're just going to use the plane polar in the 2 dimensions. This won't really come up until chapter 6 or 7 when we do circular motion, but we will use some trigonometry for vectors from the very beginning. So we're going to go over that, and then we'll go over a little bit about calculus. I know that's quick on the coordinate systems, and you have a couple questions in the homework to sort of refresh your memory. If you're having trouble with this, you really need to come see me right away, okay? Because we jump off in chapter 2, or rather chapter 3, using plane polar coordinates and trigonometry pretty soon. So if you have trouble with that, then please come see me. I know that there are some of you that are having trouble with it, like right now. So if that's the case, come sit with me for 10 minutes and we'll figure it out. I'll get you all squared away. Okay? All right. If you just don't want to come see me, also, I think I've said this before, but in the tutoring center, they do have a physics tutor, Amber Moore. She's had this class. She did extremely well in it. She's a good tutor. She's a really good teacher, too, I understand. And she's a pretty good soccer player. So she's an excellent soccer player, actually. So you can go see her. The tutoring center on campus is only $25 a semester, and that covers all your courses. So if you're in Calc 1, as many of you are, if you're in chemistry, it'll cover all those courses as well. All right. Let's see, where was I? Okay. It's probably been a long time since you've had trigonometry. Fortunately, we don't use a whole lot of trig, but we do use trig a lot. But the trig that we do is pretty limited. We just do right angle trigonometry. And so I just want to review that quickly. This is a right triangle. Right triangle, of course, has a 90-degree angle. When I'm defining an angle, like if I define the angle theta right here, I can describe the sides that are relative to it. So if this is the angle theta, this is the opposite side, and this is the adjacent side, and this is called what? My hypotenuse, right? So y'all had this in 7th grade geometry or whatever, 8th grade geometry. So that's our right triangle. We can define the relationships between those sides by the trigonometric functions. This is the mnemonic that we use to remember it. Do y'all know what this is? SOHCAHTOA. You might have another mnemonic. I like this one. There's something about a hippie or something like that. But I like this one. This describes sine, cosine, and tangent. Right. The sine of the angle theta is equal to opposite over hypotenuse. The cosine of the angle theta is equal to adjacent over hypotenuse. And the tangent of the angle theta is equal to opposite over adjacent. I'll give you a clicker question in just a second. You can practice this. Just make sure you remember how to do this from whenever the last time you did this was. We will do a lot of right angle trigonometry in this class because we deal with vectors a lot, and when you're dealing with vectors, you need to use a lot of trig. We'll always be in the degree mode on your calculator. So under modes, usually on the TI, you can set it either radian or degrees. I understand for your calculus class, sometimes you'll have it in radian mode. Make sure that you always put it back to degree mode. There might be a case in chapter 7 when we go to radian mode, but always be very clear that if you need to be in radian mode, that you are. So I'm not even sure that we need to do that for chapter 7, I forget. Okay? I remember when I was in college, I wrote a little note up at the top of my calculator. Check the mode, because I don't know how many questions like that just because I have my calculator in the wrong mode. Right? Fortunately, when I write my multiple choice questions, usually I go through and I make common mistakes and I put those as answers for those questions. I don't typically do that for mode. And actually in this class, the multiple choice are usually just conceptual, so there usually aren't any numbers involved anyway. So. All right. Now, for the Pythagorean theorem, it says that the sum of the squares of the two sides of the triangle, that is x squared plus y squared, is equal to the square of the hypotenuse, which I labeled it up there as r squared. You might see this sometimes as a squared plus b squared equals c squared, where we have these sides a, b, and c. All right, that's Pythagorean theorem. We'll use that in just a few minutes to find a triangle. And then sometimes we'll often need to find the angle theta. To do so, we remember that tangent of theta is TOA, right? TOA, so it's opposite over adjacent. So say, for example, I have a triangle that looks like this. I have a side here that's 3 units long, a side here that's 4 units long. If I want to know this angle, theta, somebody, are y'all try calculating what is that angle theta? To do so, you'll do the inverse tangent. So you take the inverse tan of this side, that gets rid of that tangent, and then you also take the inverse tangent of this side. So in your calculator, you will put in inverse tan of opposite, which is 3, over adjacent, which is 4. So y'all just give that a shot. Make sure that you're doing this properly in your calculator. On your TIs, it's going to be second. And then the tangent function, you'll see up above the tangent function, I think it says tan to the minus 1 or a tan or something like that. And then you can give me a shout out what the angle is. 37. It's 37 degrees. Everybody got 37? Yeah. Yeah, just make sure you know how to do that. It turns out the angle is 37 degrees. And then we can go ahead and find out the hypotenuse length. Oh, some of you probably know what the hypotenuse length is for this triangle. What is it? 5. Very good. Yeah, so it's a special triangle. It's a 3, 4, 5 triangle. I like to use special triangles because it makes your math a little easier on the problems. So you'll need to learn, or you don't have to. I mean, you can always just know how to use the Pythagorean theorem. And that is, if I wanted to find that side C, I would just say it's the square root of 3 squared plus 4 squared, which is square root of 25, which is equal to 5. So that hypotenuse on this special triangle is 5 units long. It's a 3, 4, 5 triangle. And then the small angle is always 37 degrees, and this angle, of course, is 53 degrees. That's 90 minus 37. So I like to use special triangles just because then you don't have to think about the math, you just have to think about the physics. All right? That's exciting, right? All right. Let's keep moving on. We'll have some questions for you to practice this in just a few minutes. All right, here's one right here. So consider this figure. First, I want to know what is R for this figure. R is the length, like in the plane polar coordinate system. R is the length from here to here. And I give the X and the Y coordinates. So I want to know what is the length R. You're going to use the Pythagorean theorem to find R. You can draw a little triangle here, just like this. It's about 15 more seconds. $145. Just guess if you don't know. All right, B is right. Very good. So we just use our Pythagorean theorem. Square root of 3.5 squared plus 2.5 squared, and that gives me 4.3 meters. In the next question, I want to know what is the angle theta. Now notice that the angle theta goes around like that. So I'm going to pull up the answers. I'll write the answers up here. I know y'all can see everything there. So I want to know what is the angle theta. There are only 3 options. theta is measured from the positive x-axis in a counterclockwise direction. That's the typical way to measure angles, unless you say otherwise. Just a few more seconds. I'll stop at 125. Looks like everybody's in. You're right. C is the right answer. Let me show you the hard way to do this, which is the way most of you did it, I think. Here's my triangle. This side is 2.5. This side is 3.5. This is an angle, I'll call it phi. This angle is not theta, right? It's phi. And the inverse of phi, or excuse me, the tangent of phi is opposite over adjacent. That's 2.5 over 3.5. And if you take the inverse tan of both sides, then you can find phi, which is going to be 36 degrees. All right. However, that's not the angle that we're looking for. We're looking for the angle from the x-axis. So I add 180 to phi. So theta equals 180 degrees plus 36 is 216, which was C. Most of you put C. However, there's a much easier way to do this, right? Because we know that the angle has to be in which quadrant? Yeah, in the third quadrant, right? So remember your quadrants from geometry. We'll use those periodically. What quadrant is this? 1. What about this one? 4. Right, this is the 4. So there's 1, 2, 3, 4, counterclockwise. This is our third quadrant. It lies between 180 degrees and 270 degrees. So we know that the answer has to be between 180 and 270. When you're doing multiple choice tests, are there any pre-med here? I don't think there are. Pre-med? No. Well, GRE and stuff like that, when you have multiple choice tests, it's very useful to be able to go through the answers and say, well, this one doesn't make any sense, this one doesn't make any sense, this one's way too big, way too small. And then sometimes you don't even have to work through the problem. You can just say, well, this has to be the answer. So that would be a good tack on this one. All right. How are we on this so far? It's largely been geometry and trig. I've sort of gone through it quickly, but we're going to use it a lot this semester. You'll use your trig functions, you'll use your Pythagorean theorem. We'll do some basic geometry, like, the sum of all the angles in a triangle is 180, stuff like that. Okay on this? If you're not, please come see me. I can help you with it. We can get you up to date. How many of you are in calculus right now? Basically everybody, is that right? How many of you have not had calculus? Okay, good. So we're going to get into some Calc 1 and 2, and then later in the semester we'll get a little bit of Calc 3. But I'm going to give you everything that you need for, I won't rely upon your calculus class to give you what you need. So most of the derivatives and integrals we do will be pretty simple. And then when we get into chapter 6 or 7, we'll do a little vector calculus, which you don't get to until Calc 3. But again, it's fairly straightforward. And then also later we'll get into a little bit of linear algebra, doing matrices and what have you. All right, so first, derivatives. Derivative is defined like this. It's a limit of delta x over delta t as delta t approaches 0. And we'll talk a lot about what this means physically, because derivatives are often used in kinematics to describe the relationship between displacement velocity and acceleration, because they're all related to one another by a derivative. Each is a derivative of another. Right, so that's our definition of a derivative. Say you have a graph right here that is a actually, let me draw another graph. We'll come to that one. Say if I have a plot of x over t, and let's say that that plot looks, it's a straight line like this. The derivative just gives the slope of that line. And in fact, it gives the slope of the line at a particular point. So the slope of this line is rise over run, which is delta x over delta t. Right? So this limit is just the limit of the slope. But the derivative is interesting or special because it allows this part, the denominator, delta t, to get infinitesimally small. That's what this means, that delta t approaches 0. So it's not just asking what is the slope of this graph, it's asking the slope of this graph at a particular instant. Right? So it takes this delta t and it collapses it down to a particular point so that you can know the slope of that graph at that point. Now this one is a simple graph because it's linear, but when you're dealing with more complicated functions, that can be very useful to find the slope of your graph at a very particular point. Right? So that's the definition of a derivative. I'm never going to ask you to spit out the definition of a derivative, but it's a useful thing to know. It's just the slope at a particular point. So we would show this, so for example, on a nonlinear graph like this, if we wanted to draw the slope of this graph at a particular point, we would draw the tangent line. And I always like to think of like a tangent line as being balanced, like a seesaw, balanced at a particular point. There is a mathematical definition. I don't know what it is exactly. It's something about the distance from the line on each point as it goes away from the point, that they're equal, the distances are equal. But I always like to think of it as like a seesaw, and it's balanced at that point. So for example, if I had a tangent line right here, that's a pretty straight line. It would look like that. But if I had a tangent line right here, it would be basically horizontal. We'll draw a lot of tangent lines, and they're going to represent the slope of that graph at that particular instant. They'll represent the derivative. Now, derivatives are pretty simple if you're dealing just with polynomials. That is just some variable to a power. And that's mostly what we're going to use in this course. So let's say that we have a function that's some constant b times t to the n. Then the derivative of that is going to be b times n times t to the n minus 1. All right, so say, for example, I have this on the next page. Yeah, say, for example, I have x of t equals 3t cubed. Remember, the derivative is b times n times t to the n minus 1. Well, here b is 3. N is also 3, so I'm going to have 3 minus 1 times t to the 3 minus 1. So that's going to be 6t squared. So that's my derivative of a polynomial. And mostly we're just going to be dealing with polynomials. Later in the semester we might use trig functions as well, but we'll address that when we get there. Okay? Oh no, we're going to address that here. We'll also look at the chain rule. Oh yeah, I'm sorry. Yes, thank you. I was mistaken. Yeah, there should be no minus 1 there. So you're right. This should be 9. Thank you both. All right. All right. Well, let's try this clicker question. What is the derivative of this function? So you just say 3 times the exponent. You all see this okay from back here? Okay. See that okay? Alright, so a few more seconds. I'll stop at, say, 125. Looks like we're still missing one person out there. Alright, that's got to be right. Let's see. Negative 6t. Yeah, so you say negative 2 times 3, the exponent times the coefficient, times t to the negative 2 minus 1, which is t to the minus 3. So negative 6 times t to the minus 3. Y'all haven't gotten to this yet in calculus yet, have you? Calc 1. But you had it in high school, like calculus in high school, maybe? Okay. Yeah, this is pretty basic Calc 1 stuff. You should get to it soon. As I said, I don't know if we're going to get to oscillations. We might replace it with another chapter. But if we get to that, we'll also be doing derivatives of trigonometric functions. I'm just going to sort of list it here. The derivative of the sine function is cosine. So the sine of some variable u is equal to the cosine, the derivative, and the derivative of cosine is the negative sine of u. We'll revisit that again if it comes up, as it probably will later in this semester. And then sometimes you might need the chain rule. Not so much for a while, like really just in one chapter we might use the chain rule. But the chain rule is pretty fundamental to Calc 1 in taking derivatives. And I know when I was a student, like I just felt like I never really got the chain rule. But it's pretty simple, so I just want to give it to you here just for the sake of having it. The chain rule says that a derivative of some variable x with respect to t is the same as dx du times du dt. So you can think about these du terms just canceling out, and then these two sides of the equation are equivalent, right? They're both dx dt. So let's try this example. Let's say that I have this function, x equals 2 cosine t squared plus 3. Hello? That's okay. All right, here I want to define what u is. So I'm just going to let u equal what? I know you might use the chain rule. Y'all remember from Cal? What's that? Yeah, that's right, Brittany. T squared plus 3, right? That's what you're trying to say. Yeah, so u is t squared plus 3. And you just let that equal u. And then you can rewrite it as x equal 2 cosine u. All right, I know that if I want to find dx, or if I want to find dx dt, rather, I start with the chain rule, which is dx du, du dt, and that's going to be the derivative of 2 cosine of u du. So that's this dx du that I've written there, and then du dt is dt squared plus 3 dt. And so this is my du dt, because I let u equal t squared plus 3. And then I have two derivatives that I take, and when I take the product of them, they're going to equal dx dt. Again, not something that you're going to be tested on right away. When we get into oscillations, we'll be taking derivatives of trig functions, and this will become useful. We'll revisit it then. But I just want to repeat it because it's a very useful rule to use in finding derivatives. All right, and so the derivative of 2 cosine u is negative 2 sine of u. And the derivative of t squared plus 3, what is that equal to? Just 2t, right? So the derivative of that is 2t. That would be like 2 times t to the 2 minus 1, and then 0 times 3, because it's assumed that there's a t to the 0 right here. So 0 times 3 times t to the 0 minus 1, which is just 0. So the derivative of a constant is 0. All right, and then I can make my substitution for u, and I find that the answer is negative 4t sine t squared plus 3. So that's the chain rule. Something we won't use till later in the semester, but a very important rule. So hopefully, if you haven't gotten it in calculus, hopefully you'll pick it up here because it's a useful thing to carry on into grad school or whatever it is that you decide to do. P-Chem, such for you chem majors, you'll use it later. All right, we're almost wrapped up with this chapter. We're going to look at some basic integral calculus. How many of you are in Calc 2 now? You're in it? How many of you have had it? Okay, just a couple of you. All right, so we're going to do some basic integrals. The integral is defined in this way. And I'll write it here. I won't ever write it again. But it's the limit as n approaches infinity of the sum from I equal 1 to n of some function f of ci times delta x. The product of these two numbers is like the area of one of these bins. Right? It's like the length times width of the area of a bin. And what you're doing here with the summation is you're adding up a bunch of bins underneath a function. And so the integral gives you the what of a curve. The area under a curve, right? So the integral, whereas slope, our derivative gave you the slope of a curve, the integral now gives you the area under a curve. And that can be very useful, as we'll see when we get into kinematics, because the area will tell us something about the motion of an object. All right? So if I want to take the integral, I'm just finding the definite integral, meaning you have these set points on either end, I'm finding the area under the curve. All right? And that's what we're doing here. These two products are the product of these two numbers, is the area of a particular bin under that curve. The width of that bin is given by the CI, by the way. And then I take the sum of it, letting n going to infinity. That means that I make those bins infinitesimally small, and then I add up the area, and it can give me the actual area under the curve. This is pretty easy to compute, too. If you take like a numerical analysis class, you'll have to do this. There's some really easy algorithms to calculate the area under a function, but you can probably figure it out. I mean, you just do length times or width times height, and that'll give you the area of the bins, and then you just add them up. You can do it in Java, C, whatever your programming language is. You can do it in Excel to calculate the area under a graph as well. All right. We'll use definite integrals. So here, this is just a picture of how you would compute the integral numerically. You would have a certain function, and then there are different ways that you can do this depending on how you define it. You just calculate the area of each of these blocks. We might have an opportunity for you to do that later if you're interested, maybe for some extra credit or something in your class, where you actually create an algorithm to calculate the area under a curve. Now, when I was a student, this kind of stuff I found to be very useful because when I went into graduate school, it's really a skill that I carried into grad school, being able to program things and calculate values from functions and what have you. And calculating the integral is just, like I said, a very useful skill. Any of y'all take numerical analysis here or something similar? I don't think y'all are required, right? Not the geomatic students, y'all have to take a computing course other than just like intro to computers? No? Okay. All right. We'll be doing definite integrals like this, or indefinite intervals rather. When I want to take the integral of a function, it's going to be 1 over n plus 1 times x to the n plus 1. Okay, so for example, let's see, I think I put it on this next one. Yeah, if I have the integral of 3x squared, it's going to be n plus 1, or excuse me, 3 times 1 over n plus 1 times x to the n plus 1. Which is just, this will cancel with this, it'll just be x cubed. Okay, we're We're going to do integrals in the next chapter, and we're going to use this rule, that 1 over n plus 1 times x to the n plus 1. We'll use that to take the integrals. If you need, I'll remind you at that time, but this is how we find the integral. Let's say that we have a function, say v is equal to 2t squared. This is a velocity versus time graph. If I plot this, it's a quadratic function, it's a parabola, right? I have v equals 2t squared. It looks like that. It's plotted in Excel. I want to estimate the area of this graph from t equals 0 to t equals 5 seconds. So I want you to go ahead, if you have your book, or even if you don't, you can sort of sketch it out and estimate the area from t equals 0 to t equals 5 seconds. To do so, you want to find the area of these individual blocks, and then you can add them up. And then you have some fractions of blocks that you can add up as well. So the area of these blocks are what? What's the area of these blocks? 10, right? They have an area of 10. The units would be meters per, meters. So each block has an area of 10. Just estimate what is the total area under the curve. On the next test, you very much will have a graphic type question. We'll get into these in chapter 2. There's something similar to this, where I ask you to find particular values from the graph, one of which might be area like this. After you estimate it, go ahead and take the integral of that function, like we did before. And if you know how to do this, evaluate it from 0 to 5 seconds. I'll do this on the board in just a second. Have I got an estimate of the area for me, roughly? Oh, yeah, you didn't estimate that, did you? Okay. What's the area? Somebody estimate it? You got what? 80, yeah. So a good estimate is 80. 83 is the actual area, right? But just an estimate. If each of these are 10, that one I've already marked as 1 or 10. Here's 20, 30, 40. Look, I can combine these two to make 50. We'll call this one that's 60, 70, and then we'll combine these two to make 80. So a good estimate of the area is 80, right? And then if we actually do the integral, as some of you already done, and evaluate it from 0 to 5, then we'll find that the area is actually 83, which is pretty darn close. So the integral of 2t squared with respect to t, and we're going to evaluate this from t equals 0 to t equals 5. I'll show you what that means. It's going to be 2 times 1 over n times 1 over n plus 1 times t to the n plus 1, which is going to be 2 plus 1. I'm going to evaluate this from t equals 0. That's my initial condition, to t equals 5, which is my final condition, or my ending point. It's going to be 2/3 t cubed from 0 to 5. What this means is I'm going to plug in pi to this function, and I'm going to plug in 0 to that function. I'm going to take the difference between those two. So it's going to look like this. 2/3 5 cubed minus 2/3 0 cubed. And as some of you already said, you can do this in your TIs, and that's equal to 83 meters. By the way, I'm okay with you using your calculators for that function. I know that all your calculators can do derivatives and integrals, but on the test, to get full credit, I need to see your work. So if you just write a number, you're not going to get credit. I want to see the work that you do to get that. So I want to see actually how you found the integral. But I recommend using your calculators. It's a good way to check your answer, make sure that you got it correct. All right, let's do a clicker question. What is the integral of this function? I think we'll probably wrap up here. That's the end of chapter 1. Remember my integral, the integral of bt to the n dt is b over n plus 1, t to the n plus 1. All right, just a few more seconds. Maybe go to 140, 140. All right, okay, yes, pretty sure it's right. So it's going to be 3 over negative 2 plus 1 times t to the negative 2 plus 1, which was, what was that, negative, it was a, right? Isn't that what I marked? Yeah. All right, folks, y'all have a good weekend. Next time, we'll pick up with some clicker questions, just reviewing chapter 1, but then we're going to move right into chapter 2. The first exam is going to be chapter 1, but like I said, just not a whole lot from chapter 1, but then chapters 2 and probably part or all of chapter 3. All right? Have a good weekend. I'll see you on Monday. If you're having trouble with this, come see me. All right, I'll post the screencast right now.